Okay, what all did we do in the last class? We have completed with the Bowers model, right? So you need to remember all the formulae which we had done in Bowers model. We did the energy associated with the electron, we did the velocity associated with the electron, the angular momentum, then we did the radius, which Bower gave us a formula to calculate the radius of the orbit in which the electron was present, and then we also did the number of spectral lines. How do we calculate? Okay, and we did the calculation of the wave number. Now today we are going to discuss 10 questions which come from this section, and in your competitions, definitely one question is going to come from this section. This section is very, very important. So what you can do is that in your notebook, when you have started doing all these notes and all, where you have put all these notes, in one column on the right hand side, you can make a column and put all the formulae. So every time when you revise this chapter, before revising the chapter, you revise all the formulae. Because from this topic, definitely one numerical that comes up. Okay, so we had done quite a detail. We did the entire Bowers model. Let's go on to the questions today. The first question is, calculate the wavelength and energy of radiation emitted for the electronic transition from infinite to stationary state of hydrogen atom. Given R is equal to 1.09678 into 10 raised to the power 7. And H is equal to 6.6 into 10 raised to the power minus 34, and C 2.9 into 10 raised to the power 8. Okay, so now in this question they have given us two states. One is the stationary state and one is infinity. Okay, so over here N1 for hydrogen, that is equal to 1, that is the stationary state, and N2 that will be equal to what? That is equal to infinity. So we apply the formula 1 upon lambda, that is equal to R 1 upon N1 square minus 1 upon N2 square. This is the formula. The value of R is also given to you. Okay. So value of R, that is equal to what? 1.09 we can take approximately into 10 raised to the power 7. This is the value of R given to you. Okay? Upon 1 upon N1 square. 1 ka square, and at infinity means what? 1 upon N2 square is 1 upon infinity square. This is how you can put it. Okay? So lambda, when you are going to calculate 1 upon infinity, that will become equal to 0. Right? So we have 1 upon lambda, that is equal to 1.09 into 10 raised to the power 7. Right? Or lambda will be equal to reciprocal of this 1 upon 1.09 into 10 raised to the power 7. Okay? So when you calculate this comes to 9.11 into 10 raised to the power minus 8 meters. Right? So this is lambda. Then the second part of the question is that we need to calculate energy. We know that energy is equal to HC upon lambda. The value of H given to you in the question is 6.6256 into 10 raised to the power minus 34. So we can take it approximately as 6.6. Right? Into 10 raised to the power minus 34. Velocity of light is given as 2.9. 2.9 into 10 raised to the power 8. So into 2.99 into 10 raised to the power 8 upon the value of lambda. The value of lambda can be taken from here. It is coming as 9.11 into 10 raised to the power minus 8. Right? So when we calculate this, E comes to 2.17 into 10 raised to the power minus 18 joules. So this is how this question had to be done. In the first step, calculate the value of lambda, then put in the value of energy, that is E is equal to hc upon lambda, and you can calculate energy. Right? So this was a simple question. Let's go to question number 2. Question number 2 is calculate the velocity in centimeters per second of an electron placed in the third orbit of hydrogen. So n is given 3. Also calculate the number of revolutions per second that this electron makes around the nucleus. Okay. So first of all, in the first step, we need to calculate the radius. Only then we can calculate the velocity. So in the first step, let's calculate the radius for n is equal to 3. Radius that is given as what? 0.529 into n square. Okay. So this is in what? 0.529 Armstrong. Okay. So if you want to convert it into centimeters, that will be 10 raised to power minus 8 centimeters. Okay. So this is 0.529 into 3 ka square, which is equal to 9 into 10 raised to power minus 8. Right? So this when calculated, it comes to 4.761 into 10 raised to power minus 8 centimeter. Okay? This is R. Then after that, we will now calculate the velocity. Velocity can be calculated by the formula mvr is equal to nh upon 2 pi. Okay? Or velocity that will become equal to nh upon 2 pi mr. Right? The value of n given to us is 3 into 6.6. The value of h we can take as 6.6 into 10 raised to power minus 34 upon 2 into 3.14 into value of mass of the electron, that is equal to 9.11 into 10 raised to power minus 28 grams. Minus 28. Okay? And into radius, which we had found over here. So radius that is equal to 4.761 into 10 raised to power minus 8. Okay? So this when calculated, the velocity that is coming to 0.729 into 10 raised to power 8 centimeters per second. This is velocity. Then the third part of the question is we have to calculate number of revolutions per second. So the formula for that would be number of revolutions per second, that is given by 1 upon 2 pi r upon velocity. Okay? So this comes to velocity upon 2 pi r. Let's put in the values. The velocity that is 0.729 into 10 raised to power 8. Okay? And 2 into 3.14 into r. The value of r, that is how much? 4.761 into 10 raised to power minus 8. 4.761 into 10 raised to power minus 8. Okay? So this when calculated, it is coming to 2.4 into 10 raised to power 14 revolutions. 14 revolutions per second. This is an important question. Okay? Maybe itna lamba nahi aayega, it won't be so long, but still you've got a new formula over here, which is number of revolutions. So you might get the velocity to you is given to you in the questions, and they ask you to calculate the number of revolutions per second. Clear? Okay, then let's go on to question number 3. Question number 3. What is question number 3? the electron energy in hydrogen atom is given by E is equal to minus 21.7 into 10 raised to the power minus 12 upon n square erg. Calculate the energy required to remove an electron completely from n is equal to 2 orbit. What is the longest wavelength of light that can be used to cause this transition? So what has been given to you in the question is, they have given us the value of energy, which is how much? Minus 21.7 into 10 raised to power minus 12 ergs upon n square ergs. This is the value of energy which is given to us. Okay. Now electron, they are saying that electron energy in the second orbit we have to calculate. So if we have to calculate the energy of the electron in the second orbit, n will become equal to 2. Okay? So we have minus 21.7 into 10 raised to power minus 2 upon 2 ka square, which is 4. Right? Now energy at infinity, because we have to extract the electron, energy at infinity, that is going to be equal to 0. Then that we had already done. Okay? So delta E will be equal to what? E2 minus E1. So E infinity minus E2. Okay? E infinity, that is equal to 0 minus 21.7 into 10 raised to power minus 2 divided by 4. Sorry, 2 near 12. Okay? Divided by 4. So energy when calculated over here, that comes to 5.425 into 10 raised to power minus 12 ergs. Because in the question also it is given to us in ergs. So over here also we will put the same unit. Okay? Now delta E, that is given to us over here. We know that delta E, that is equal to HC upon lambda. Okay? So lambda would be equal to what now? HC upon delta E. Let's put the values. The value of H is 6.6 into 10 raised to power 34 into 3 into 10 raised to power 8 upon value of delta E, that is 5.425 into 10 raised to power minus 12. Okay? That is lambda. So lambda when calculated, that comes to 3.7 into 10 raised to power minus 5 in centimeters. 3.7 into 10 raised to power 5 minus 5 centimeters. Right? So this is the longest wavelength which can cause this transition. Have you understood? So for this, first you needed to calculate delta E and henceforth you calculate lambda. Got it? Okay. Let's go to next question. Question number 4. Question number 4. The fourth question is, calculate the shortest and the longest wavelengths in hydrogen spectrum of Lyman series. And it has been put in another form. Or calculate the wavelength of the first line and the series limit for the Lyman series for hydrogen. Both the questions have the same meaning. Okay? So what are they asking? Calculate the shortest and the longest wavelengths in hydrogen of Lyman series. Now when we are talking for Lyman series, they have asked us to calculate for two transitions, the longest and the shortest. Okay? For Lyman series, N1, that is going to be equal to 1. Right? Now when N1 is equal to 1, the shortest wavelength we have to calculate. For shortest wavelength, what will happen? The energy is going to be maximum. So it is going from 1 to infinity. Right? So that is the shortest wavelength we are going to get. For shortest wavelength N2, that is going to be equal to infinity. So 1 upon lambda, that is equal to R upon 1 upon N1 square minus 1 upon N2 square. The value of R, that is 109677. Okay? Or you can also put it as 1.09677 into 10 raised to power 1, 2, 3, 4, 5. Okay? Into 10 raised to power 5. We can take this into 1 upon 1 square minus 0. Right? So this is going to come as what? Same. Into 10 raised to power 5. Right? So lambda will be reciprocal of this. 1 upon 1.09677 into 10 raised to power 5. When we calculate this, it comes to 9.11 into 10 raised to power minus 6 centimeter. Okay, then in a similar manner, you can calculate it for longest wavelength. For longest wavelength, N1 that is going to be equal to 1 and N2 that is going to be equal to 2. Right? So we have 1 upon lambda that is equal to R, 1 upon N1 that is 1 square minus 1 upon 2 square is equal to 109677 upon 1 minus 1 by 4. Okay? So this will become equal to 109677 into 3 by 4. Okay? And lambda will become equal to reciprocal of this. So we can take this as 4 upon 3 into 1.09677 into 10 raised to power 5. This is how we can put it. Right? So when we calculate lambda for this, it comes to 1215.7 into 10 raised to power 8 centimeter. Right? And you can convert it into Armstrong if you want to. Both could be converted into Armstrong. So when you are converting it into Armstrong, lambda 1 that will become equal to 911. This is minus 6, so you displace the decimal from here by 2 places. It will come as 911.7 Armstrong, and this will become equal to 1215.7 Armstrong. Okay? So let's go on to the next question now. Question number 5. The question is, light of wavelength 12818 Armstrong is emitted when the electron of hydrogen atom drops from 5th to 3rd orbit. Find the wavelength of the photon emitted when the electron falls from 3rd to 2nd orbit. So one of the lambda is given to you. Okay? So what do we have to do over here? We have to calculate the lambda of the second. So let's see. We know that 1 upon lambda that is equal to R 1 upon N1 square minus 1 upon N2 square. Now remember always that the value of N1 is always smaller than N2. Right? So if you have some confusion in the question, what value has to be taken for N1 and what value has to be taken for N2, always N1 is going to be smaller than N2. Okay? So over here, the first transition given to us is N1 is 3 and N2 is 5. So we have, and lambda is also given to us how much? 12818 Armstrong. 12818, that is equal to R 1 upon 3 and 5 is given to us. 3 and 5. So 1 upon 3 square minus 1 upon 5 square. This will become equal to R 1 upon 9 minus 1 upon 25. ठीक है? So this when calculated it comes to what? It will come to 16. So it comes to R 16 upon 9 into 25. That is what we are going to get over here. ठीक है? Now when we calculating lambda over here, or we take the reciprocal, then by taking the reciprocal, what will we get? 12818. We are going to get 9 into 25 upon 16R. ठीक है? Now let's similarly calculate for the second transition. For the second transition, n1 is equal to 2 and n2 is equal to 3. ठीक है? So now lambda is not given to us over here. We have to calculate lambda. So we have 1 upon lambda, that is equal to R 1 upon n1 square minus 1 upon n2 square. ठीक है? So this will become equal to R 1 upon n1 का क्या हुआ? 2 2s are 4 minus 1 upon 9. So this will become equal to 5 upon 36 into R. ठीक है? And lambda will become equal to what? This is 1 upon lambda. So lambda over here, that will become equal to 36 upon 5R. Let's say this is equation 1 and this is equation 2. Right? Now you divide equation 2 by equation 1. Divide equation 2 by equation 1. So when you are going to divide equation 2 by equation 1, we will get lambda upon 12818, that is equal to 36 upon 5R divided by 9 into 25 upon 16R. This is what we are going to get. ठीक है? So let's calculate over here. We will get 36 upon 5R into 16R upon 9 into 25. This and this gets cancelled. 9 4s are 36. Right? So when we are calculating lambda over here, lambda comes equal to 6562.8. 6562.8 Armstrong. ठीक है? Clear? So this is how you are supposed to do this question. Then let's go on to the question number 6. Question number 6 is the ionization energy of hydrogen atom is 13.6 electron volt. What will be the ionization energies of He2 positive and Li2 positive ions? Now when we are talking of ionization energy that is minus the energy of electron in any orbit. This is what we have studied. ठीक है? That is why the ionization energy is same as the energy of the electron but with a positive sign. Okay? So this is what ionization energy is. Now energy of the first orbit, that is going to be what? That is going to be minus 2.18, or if you are talking of let's calculate it in electron volts. So if you're talking of electron volts, that is minus 13.6 upon 1 square. Okay, so that is equal to minus 13.6. Right? In a similar manner, when we are talking of energy of the first orbit of helium, then it will become what? Then the formula given is 13.6 upon n square into z square. ठीक है? Atomic number of helium that is equal to 2. So this will become equal to minus 13.6 into 4. ठीक है? So when you calculate this, that becomes equal to 54.4 electron volt. Got it? This is the energy for helium. In a similar manner, first orbit of lithium also you can calculate. Then that will be equal to what? Minus 13.6. The atomic number of lithium, that is 3. Right? So into 9. This when calculated, it comes to minus 122.4. electron volt, right? Then what is going to be the ionization energies now? When we talking of ionization energy over here, it will have the same value of ionization energy, but that is going to be positive. So let's say that the ionization energy for hydrogen, that is going to be equal to 13.6 electron volt. Similarly for lithium, for helium it is 54.4 electron volt, right? And for lithium it is going to be 122.4 electron volt. Have you understood? So if you get to calculate the ionization energies, in that case what we have to do is we only have to change the sign. We have to calculate the energies first by this method and then you change the sign. Ionization energies, they are going to be positive. Okay, then let's go on to question number 7. Question number 7. Question number 7 is, if the energy difference between two electronic states is 46.12, what will be the frequency of light emitted when the electrons drop from higher to lower states? And they have given us the value NH is equal to 9.52 into 10 raised to the power minus 14 kilocalories second per mole, where N is the Avogadro's number and H is the Planck's constant. Okay. Now what have they given to us in the question? Delta E is given to us, the energy of transition, that is 46.12 kilocalories. Per mole, right? Now Bohr says what? That delta E, that is equal to h nu. Delta E is equal to h nu. Now according to when we are talking of 1 mole, so for 1 mole delta E, that will be equal to NH nu. Okay? The value of NH is given to us. How much? 9.52 into 10 raised to power minus 14. 9.52 into 10 raised to power minus 14 nu, and the value of delta E, that is 46.12. Now you have to calculate the value of nu, so nu that will become equal to what? 46.12 divided by 9.52 into 10 raised to power minus 14. That is nu. So nu becomes equal to what? 4.84 into 10 raised to power 14. Per second is the unit. ठीक है? Done? Okay. then let's go on to question number 8. Question number 8. Question number 8 is, according to Bohr's theory, the electronic energy of hydrogen atom in the nth orbit is given by En is equal to minus 21.76 into 10 raised to the power minus 19 joules upon n square. Calculate the longest wavelength of light that will be needed to remove an electron from the third orbit of He positive ions. Okay? First of all, let's calculate the electronic energy of He positive ions. Right? When we are calculating it for He positive ion, then for the second orbit we have to calculate. So E that will become equal to what? What is the value of energy given to us? Minus 21.76 into 10 raised to power minus 19 upon n square into z square. Okay, let's put the values. So n over here they have given us third orbit. So we have minus 21.76 into 10 raised to power minus 19 upon n square. The value of n is given 3. So 9 and atomic number for helium is 2. So 4. Okay? So when we are calculating this, the value of this will come as what? Let's not calculate because we have to calculate lambda in the question, longest wavelength. So let's keep it like this only. Okay? Now when we are talking of ionization energy of this, then we will get a positive sign over here. That is the difference. So we say that ionization energy or the energy required to remove the electron from this state, that is going to be minus 21.76 into 4. So this is going to be positive. Okay? So this is the ionization energy. Now what is lambda? Epsilon delta E, the value of H, that is 6.6 into 10 raised to power minus 34 into 3 into 10 raised to power 8 upon value of delta E, that is this. So this will be 21.76 into 10 raised to power minus 19 into 4 into 9. Okay? So when you calculate lambda over here, lambda comes to 2.055 into 10 raised to power minus 7 meters. You have to be very particular in your multiple choice questions with regard to the units also, because sometimes all the values given the same but the units are different. So then it is very important for you to know कि कौन सा unit choose होगा. ठीक है? Okay, then let's go to question number 9. Question number 9. Question number 9 is, calculate the energy emitted when electrons of 1 gram atom of hydrogen undergo transition, giving the spectral line of lowest energy in the visible region of its atomic spectrum. RH given to us is 1.1 into 10 raised to power 7 per meter. C is also given and H is also given. Okay? Now over here, when we are talking of, the question is telling us that the transition is in the visible region. So if the transition is in the visible region, the value of n has to be taken according to what? The Balmer series. ठीक है ना? So Balmer series we have to take over here. Transition will occur like Balmer series. So Balmer series में n1 that is going to be equal to 2 and n2 will be equal to, because we are talking of the lowest energy. So lowest energy is going to be 2 to 3. ठीक है? So we have n1 over here 2 and n2 that is equal to 3. So let's put the formula 1 upon lambda that is equal to 1.1 into 10 raised to power 7, this is the value of r given to us over here in the question, ठीक है, into 1/2 का स्क्वायर माइनस 1/3 का स्क्वायर, ठीक है, और let's not take the value of this thing over here, चलो let's take it also, doesn't matter. So what are we going to get over here? This is going to be equal to 1.1 into 10 raised to power 7 into, this is going to be 1/4 minus 1/9, so 5/36, ठीक है, so 1.1 into 10 raised to power 7 5/36, ठीक है, clear? Now what are they asking from us in the question? We need to calculate the energy. So energy that is going to be equal to HC more lambda. Lambda is this. The value of H is 6.6 into 10 raised to power minus 34 into 3 into 10 raised to power 8 upon 1.1 into 10 raised to power 7 into 5 into 36, ठीक है, this when calculated it comes to 3.03 into 10 raised to power minus 19, ठीक है, this is the value of energy. Now over here we have to calculate the energy with respect to 1 gram of atom. That is what is asked to you in the question now. Calculate the energy emitted by electrons of 1 gram of an atom. So let's calculate the energy for 1 gram of an atom. That will be equal to what? This into Avogadro's number. Because the atomic number of hydrogen is 1. ठीक है, so number of atoms in 1 gram of any substance of hydrogen, 1 gram will have Avogadro's number of atoms, ठीक है, so for 1 gram number of atoms that is going to be equal to m0, which is the Avogadro's number. This is an important question again. So this is 6.02 into 10 raised to power 23. ठीक है? So let's multiply energy for 1 gram. That will be equal to 3.03 into 10 raised to power minus 19 into 6.02 into 10 raised to power 23. This is the energy for 1 gram. And when calculated, it comes to 18.25 into 10 raised to power 4. ठीक है? This is joules per atom. Or sorry, joules only, not per atom, joules. This is joules per atom, and this is going to be in joules. Have you understood? Okay. Then the last question. Question number 10. How many times does the electron go around the first Bohr's orbit of hydrogen in 1 second? This is your question. So number of revolutions per second is given by the formula. V upon 2 by r, ठीक है, this we just did, V upon 2 by r. So velocity that is equal to what? Velocity given is, velocity we know that is equal to 2.188 upon x square, ठीक है, so velocity will be given as what? N is equal to 1 over here, not n square, sorry, n. Velocity is equal to 2.188 into 10 raised to power 8 upon n. N given is 1. So velocity will become equal to 88 into 10 raised to power 8. ठीक है? Now you can calculate the number of revolutions. We also have to calculate R over here. R will be equal to what? What is the value of R? 0.529. Right? Now over here, n is also equal to 1 and z is also equal to 1. So R will be equal to 0.529. Let's put the values, number of revolutions के लिए. What is velocity? Velocity given to us is 2.188 into 10 raised to power 8 upon 2 into 3.14 into 0.529. ठीक है? So this when calculated, it comes to 6.59 into 10 raised to power 15. 6.59, sorry, not 19, 6.59 into 10 raised to power 15 revolutions per second. Have you understood? So these are a few important questions from this section. Tomorrow we are going to start with our next model. Okay? And I guess 2 lectures more for this chapter. Right?